All right, now we're studying Chapter 17, Electric Current, and this will be Part 2 of the Introduction to Chapter 17 on circuits. We've already had Part 1 on electric current and resistance, and now the second half of Chapter 17 is on circuits. So here's an introduction. It's sort of a review of Part 1. Electric currents flow in circuits. And that is the physics behind the electric technology that we use every day. So in this video, we're considering circuits with batteries, resistors, and capacitors connected by ideal wires. These are DC circuits. They have direct current. That is to say, the current at any point in the circuit flows only in one direction. Later, we'll consider AC circuits, which have alternating current. But for today, we'll have a circuit of some sort. It may have batteries. It may have resistors. It may have capacitors. But a battery has an EMF, an electromotive force, because a battery maintains a potential difference between the positive terminal and the negative terminal. So the electric current from a battery will just flow in one direction. In this case, clockwise. So if I look at any point in the wire, the only current is going, well, down here it's going to the left. An alternating current is different, because in an alternating current, if you look at a point in the wire, the current will be going back and forth, back and forth, back and forth. It's alternating in direction. Here's something we considered before. The circuit diagram for a battery, or for a flashlight. There's a battery, a switch, and a resistance. The resistance is in the filament of the light bulb. When the switch is closed, current I flows clockwise around the circuit. So any wire in the circuit, including the filament, carries direct current. All right, now we've studied Ohm's law before, which is current in a resistor. Now let's consider combining resistors. You know, in this circuit with the switch closed, there's only one resistance. The wires have some little trivial amount of resistance, but we just approximate the wires as ideal wires with no resistance. So there'd only be one resistor. Well, suppose we had this circuit, a battery and 4 resistors combined in this way. How much current will there be? You know, here, the current is the EMF of the battery divided by the resistance of the circuit, which is to say the resistance of the filament. What's the current here? Well, actually, there are 2 different currents. There'll be a current from the battery flowing away from the positive terminal, and the same amount of current flowing into the negative terminal. we could call that I. That's the current supplied by the battery. Now, at this point, the current I will split apart into two parts. There'll be a current I, we could call this one I1, and this one I2. And we could say I1 flows in this direction, and I2 flows in this direction. So you see, we actually have three currents, I1, and I2. However, charge is conserved. So I is equal to I1 plus I2. In the book, you'll see that referred to as Kirchhoff's junction rule. If current comes into a junction, this is the junction, this point where the circuit splits into two parts, then the current flowing into the junction is equal to the current flowing out of the junction. And that's because charge is conserved. Charge can't disappear. So if I were not equal to I1 plus I2, then charge would be accumulating at the junction. And that never happens. So you see, we have three currents, but really we only have two because I is equal to I1 plus I2. Now these currents go through various resistors. So I goes through this resistance, I2 goes through this resistance, I1 goes through this resistance and this resistance. So you see, we have combinations of resistors. And there are two combinations of resistors, series and parallel. So let's consider, for example, resistors in series. You have a current I coming in on this side. I'll get rid of this stuff. We have current I, or let's call this I1. Well, here I've used uppercase I. Sometimes current is called uppercase I, sometimes it's called lowercase I. So I have some current I1 coming into the left side, and I'll have some current I2 coming out of the right side. Well, the first thing to notice is that I1 is equal to I2. Any current that comes in on one side has to go out on the other side, because it comes in on the left side, goes through the first resistor, then it goes through the second resistor, or an equal amount goes through the second resistor, and then it flows out through the right-hand side. So if you think of I as a kind of a stream, it's just like a stream of water. Any water coming in on one side, the same amount of water has to go out on the other side. Otherwise, you'd have water piling up somewhere in the middle. Charge can't pile up someplace. So I1 and I2 are the same. Now let's suppose this resistance is R1. And this resistance is R2. Then the potential difference across the first resistor is not the same as the potential difference across the second resistor. We'll call I1 and I2 both equal to I, because they're the same. The potential difference across this resistor is IR1. Don't bark, Tommy. All right, so this potential difference is IR1. And this potential difference is IR2. And the potential difference across the two resistors is delta V1 plus delta V2. So there's a potential difference across R1, delta V1, across R2, delta V2. Delta V1 is R1I. Delta V2 is R2I. So see, the potential difference across these two resistors is I times combined resistance. And the combined resistance is just R1 plus R2. So that is the formula for resistors combined in series. Write it down in your notebook. You'll be using it. Don't bark, boy. Now, the other kind of combination of resistors for two resistors is resistors in parallel. So we have some current, let's call it I, coming to a junction where the current splits into two parts, I1 and I2, going through two different resistors, R1 in the top, R2 in the bottom. And then I flows away from the other side. So it flows in one side and out the other side. But at the junction, it splits apart into two. I1 going through R1 and I2 going through R2. There's something which is constant when you have resistors in parallel, and that's the potential across the resistors. So from here to here, the potential difference is delta V. From this point to this point, the potential difference is delta V. And that's the potential difference across this wire, or this resistor, and it's also the potential difference across this resistor. So delta V is delta V1, and it is delta V2. Because there's no resistor in the ideal wires, there's just resistance in the resistors. So the potential difference from, let's say, this side to this side is the same for the two resistors. Now, as we saw before, Kirchhoff's loop rule says I is I1 plus I2. We have I coming in this way, we have I1 going this way, and we have I2 going this way. Well, at the junction, the amount of current coming into the junction has to be equal to the amount of current going out of the junction. It's just like the flow of water. If you had a river with a fork in the river, the amount of water flowing into the fork would be equal to the sum of the water flowing on one side and flowing on the other side. So I is I1 plus I2. Delta V1 is I1, R1. And delta V2 is I2, I1 times R1, I2 times R2, These are both equal to delta V. So I1 is delta V over R1, and I2 is delta V over R2. So you see, the current is delta V divided by some combined resistance. The current is delta V over R1 plus delta V over R2. So 1 over R combined is 1 over R1 plus 1 over R2. In other words, when you have parallel resistors, the combined resistance is not the sum of the two resistances. The reciprocal of the combined resistance is equal to the sum of the reciprocals. Or we could write it a different way, combine the two denominators here. I'd have the denominator R1, R2, the numerator R1 plus R2, but that's 1 over R, so now take the inverse of that. R would be R1, R2 over R1 plus R2. So that's the rule or the formula for combining resistors in parallel. Write it in your notebook. You're going to need to know that. Now let's go back to that problem that we considered with 4 resistors. What's the overall combined resistance? In other words, for the purpose of calculating the current from the battery, I can view this as one big resistor. So here's one big resistor. It's this network of resistors. This network of 4 resistors. And the battery supplies a current I, a potential difference delta V. Well, it's just the EMF of the battery, so I'll write it as E. And I is E over R combined. Combining 4 resistors. We combine those 4 resistors into one effective resistance. R combined is R1 plus 1 over R2 plus 1 over R3 plus R4, that combination to the power minus 1. Why? Because here's R1. Well, let me just put the number. Here's R1. Here's R2. Here's R3 and R4. Now, R3 and R4 are in series. See, any current that goes into R3 also goes into R4. So R3 and R4 are in series. So the combined resistance of 3 and 4 is R3 plus R4, using the equation you wrote down in your notebook. I1 is not in series with R3 or R4 or R2 because there's a junction. I1 is in series with this combination of 2, 3, and 4. So let me annotate this with a different color. Take these 3 together. Those are in series with I1, because any current that comes into I1 also goes through this network of 2, 3, and 4, comes out the other side. So the current through I1 is the same as the current through the combination of 2, 3, and 4. Now, 2, 3, and 4 is a parallel combination of 2 and 3 and 4. And the series combination of 3 and 4 is R3 plus R4. So the reciprocal of the resistance of the network 2, 3, and 4 is 1 over R2 plus 1 over R3 plus R4. That's the reciprocal. 1 over that gives me the resistance of this 3 resistor network. That's in series with R1. So the combined resistance is R1 plus 1 over R2 plus 1 over R3 plus R4. So in other words, in analyzing this 4 resistor network, I see that R combined will be R1 plus the combination R2, 3, 4. And R2, 3, 4 is a parallel combination of 2 and the series combination of 3 and 4. So R2, 3, 4 is 1 over R2 plus 1 over R3, 4. To the power minus 1. This was R, can't read it. This was R2. And now R3, 4, well, 3 and 4 are in series. So that's R3 plus R4. So you see, in analyzing this circuit, I had to use both the rules for series combinations and parallel combinations. Now, in the Lon Kappa assignment, you'll get some practice doing this. And it'll undoubtedly show up on the next midterm exam. There's an interesting connection between resistance and the electric energy in a circuit. When electric current passes through a resistor, it loses energy. Now, of course, energy is conserved. That's one of the great unifying principles in science. So, if the electric current loses energy, the energy must go somewhere else. And this is an example of transfer of energy by heat. The energy is transferred to the atoms and molecules in the material that the wire is made of. The electrons pass through this material, but not freely. They have resistance. They collide with atomic particles, ions, other electrons in the material, because they're all charged. And in these collisions, they transfer energy to from the current flow, from the stream of current, to the random motions of the atoms and subatomic particles in the metal. And here's an important equation. The power dissipated in a resistor, say the resistance of the resistor is R, carrying current I, power is I squared R. Write it down in your notebook. You're going to need that. What does it mean? Well, if there's a current I in a resistor with resistance R, it will be losing energy, transferring energy to the random thermal motions of the atoms and subatomic particles in the metal. And the quantitative formula for power is I squared times R. Now, what are the units here? Well, the unit of power is the watt. So a watt, the unit of current is an amp. So a watt must be an amp squared times resistance. And the unit of resistance is the ohm. Or let's simplify these units a little bit. Watt is joules per second. So watt is joules per second. Let's multiply both sides of the equation by seconds. So joules is amp squared. Now amp squared is coulomb squared per second squared. But remember, I multiplied both sides of the equation by seconds. So 1 over second squared times seconds is seconds. And now times ohm. Now, ohm, remember, resistance is voltage divided by current. So ohm is voltage divided by amps. Well, actually, I shouldn't have converted amps into coulombs per second, but anyway, I've done it already. So amps is coulomb per second. The seconds cancel. Coulomb squared divided by coulombs is coulombs. So a joule is a coulomb volt. That we already know. Recall the relationship between electric potential energy and charge. The change in potential energy, or I guess I better call this delta U, the change in potential energy is Q times the change in electric potential. That's really the definition of electric potential. So delta U is joules, Q times delta V is coulomb times volts. So you see the units between this equation and this equation are consistent. So let's see if this equation makes sense. If I take this equation and multiply by a time, power times time is, well, no, I'll take this equation and multiply by time. Change in energy is power times time. Power is watts. Power is energy, in this case, the electric energy U, over time. I guess in terms of changes of energy and changes of time, power is a change of energy per unit time. Watts is coulombs per second. So let's take U and write it as power times time. And now Q is current times time. And delta V is delta V. So now divide both sides of the equation by time. Power is current times voltage. But by Ohm's law, voltage is current times resistance. So power is I squared R. So here's an interesting relationship between energy and current and resistance in a circuit. The power lost by the circuit transferred to heating. Heating is a kind of energy transfer, so I should say transferred by heating to the thermal energy of the atoms and molecules in the metal. Well, you'll have some homework problems where you have to use this I squared R formula. The final section in Chapter 17 is called RC circuits. So this will be a circuit where there's a battery, a resistor, and a capacitor. Or there could be multiple resistors or multiple capacitors. And this is a topic which you'll use in some of the law and capital problems and which will undoubtedly show up on the next midterm exam. Let's work out an example. So the example we'll work out is charging a capacitor. So we have a battery, a switch, a resistor, and a capacitor. Close the switch at time 0. What happens? Well, when the switch is closed, there'll be a current. It'll be directed out of the positive terminal of the battery and into the negative terminal of the battery. This is when the switch is closed. The current will also flow around the circuit in this direction. What's that? Clockwise. So it will flow inside the resistor and then out of the resistor. And then it'll come to the capacitor. Current can't flow through a capacitor because a capacitor has two metal plates separated by an insulator, an insulating layer. So no current can flow from one plate to the other plate. Well, it can flow around through the circuit, but it can't flow around through the gap, the insulating material in the gap. So what happens here is that charge will build up. A positive charge on this side of the capacitor and a negative charge on this side of the capacitor. In other words, you'll have a charged capacitor. Of course, the overall charge in a capacitor is always 0 because a capacitor has equal but opposite charge on the two conductors. So the total charge is 0, but there's a separation of charge into plus Q on one plate and negative Q on the other plate. Now, let's suppose you close the switch at time 0. Well, then the charge will begin to build up, and it'll continue to increase as long as there's current. So there'll be a current, but that current will vary in time. So there'll be a time-dependent current. It's a DC current. It's always going clockwise, but it's changing in time. It starts out, the instant you change the switch, the current will be well, the instant you close the switch, the current will start. But it'll eventually reach an equilibrium. It'll eventually reach 0. So if I made a graph of the current as a function of time, it would start out at some value. In fact, it will be the EMF of the battery divided by the resistance, because any current out of the battery has to go through this resistance. So the instant you close the switch, there's a way for the current to flow through this resistor. And so the current will be E over R. So there's a graph of current I versus time t. But as the capacitor charges up, the capacitor voltage will cancel the EMF of the battery. And so the current will then go to 0 as a function of time. That will turn out to be an example of exponential decay. We'll come back to that in a minute. Now, as the current starts at some value and decays to 0, the charge on the capacitor as a function of time starts from 0, assuming that we've discharged the capacitor with the switch open, and then we close the switch with a completely discharged capacitor. The charge Q starts at 0. And then it begins to build up until it reaches a constant when there's no more current. So it will build up and flatten out to some final value. When the current is 0, there's no charge being added to the capacitor. So as the current goes to 0, the capacitor charge goes to a constant. And what is this constant? Well, if there's no current, it's just like the resistor isn't present. So the voltage difference across the capacitor will have to be E, the electromotive force of the battery. And you know the potential difference across a capacitor is Q divided by C. So this final charge will be C times E. Now that's all qualitative. And now let's do the math and find the formulas for capacitor charge and current as functions of time. So we'll define I of t as the clockwise current at time t. We'll define Q of t as the charge on the right plate here. And then minus Q of t will be the charge on the left plate. As charge builds up on one plate, it has to flow away from the capacitor, leaving the other plate negative. Otherwise, the capacitor would have a net charge, and that never happens. Now, Kirchhoff's loop rule, something you need to read about in the textbook, says that the change in voltage around a circuit is 0. So let's calculate the change in voltage from this point around the circuit and back to this point. You're starting and ending at the same point, so the change in potential has to be 0, because you go from some potential, call it V, it goes around, it changes, it comes back, it's got the same value V at that point. So delta V is 0 around the loop. That's Kirchhoff's loop rule. So now let's calculate the change in potential around the loop. Well, first of all, there's the change in potential across the battery. That's the EMF of the battery. This is just if the switch is closed, this is just a pure wire, an ideal wire, so there's no potential change there. Now there's a potential change across the resistor. If current is flowing clockwise, then this must be the high potential side, this must be the low potential side, because current flows from high potential to low potential. And so the change in potential is negative from high to low, so it's negative. And by Ohm's law, it's minus I times R. And now we have the potential difference across the capacitor when it has charge plus Q on one side, negative Q on the other side. Well, this is the high potential side. This is the low potential side. High potential is near positive charge. Low potential is near negative charge. So this is from high to low, so the change is negative. It's negative Q over C. That's back to the original point. So E minus IR minus Q over C has to be 0. That's an example of Kirchhoff's loop rule. Now we have two functions we're trying to figure out, I and Q. Well, we can't figure out I and Q from only one equation. We have to have another equation. So we need another equation, and the equation is I is delta Q over delta T. Why? Because the amount of charge coming to this plate, delta Q, in a little time interval, will be I delta T. That's the definition of current. Current is charge divided by time. So delta Q is I delta T. I is delta Q over delta T. Now we have two equations with two unknowns. But one of them is a differential equation. When there's a differential equation, we also need a boundary condition, because this really only tells me how things are changing in time. In order to have everything as functions of time, I have to know one point in time. That's called a boundary condition, or sometimes called an initial condition. And I do know a boundary condition. At the instant the switch is closed, the capacitor charge is 0. This is the boundary condition. I'll put that in a different color. So here's the boundary condition. I said the capacitor starts out being uncharged. So the instant I close the switch, there's no charge on the capacitor. So that's the boundary condition. So now I have two differential equations and a boundary condition. And there's a mathematics to solve problems like that. It comes from calculus, but we don't use calculus in Physics 231. So the answer is given in the textbook. but the derivation of the answer using calculus is not given. So I had those equations, and the rest is just math, but it does require calculus. So the textbook gives us the answer. Q at time t is CE 1 minus e to the minus t over tau, where this is the exponential function. So the exponential function of some variable, let's call the variable s, the exponential function is also written as e to the power s, where e is Euler's constant. So you see there's an exponential behavior. C is the capacitance of the capacitor. E is the voltage of the battery. Tau is RC. Tau is called the time constant because it shows how the time dependence charges the battery, the capacitor. So here's again the graph. I had a graph qualitatively a minute ago, but here's a numerical graph of Q as a function of time. Or to make it numerical, I'll plot Q divided by C times E. That's a dimensionless number. That's a pure number because capacitance times voltage is charge. And to make the time dimensionless, I'll plot it as a function of time divided by tau. Tau has seconds. Time has seconds. T divided by tau has no unit. It's just a pure number. And you see what happens. The capacitor starts with charge 0, and then it grows as it's charging up, and then it flattens out. It levels off at some final value. Q over CE is 1, so Q is CE, as I figured out qualitatively a minute ago. Well, that's the charging of the capacitor. Now, what about the electric current, which is what's actually charging, providing the charge to the capacitor? The electric current is E over R, e to the minus t over tau. It's an example of exponential decay. So this is the exponential function. I'm actually plotting here I divided by E over R. E over R has units of current, so I divided by E over R has no dimensions. It's just a pure mathematical number. Goes between 0 and 1. And again, here I'm plotting the t in units of the time constant tau. And this shows what I had on the previous slide. The current starts out at V over R, or really I should say the EMF of the battery over R. So in the instant that the switch is closed, the current starts flowing around the circuit, everywhere except inside the capacitor, but in particular flowing through the battery, flowing through the resistor. And the amount of current will be the voltage difference divided by the resistance. Then it decays exponentially, eventually to 0. So here's 0. So it decays exponentially as the voltage on the capacitor increases exponentially. So when the capacitor is fully charged, the current will be 0, because the voltage across the resistor, when the capacitor is fully charged, that current is 0. The potential difference across the resistor will be the potential difference of the battery combined with the potential difference of the capacitor, But when the capacitor is fully charged, those two potential differences are equal but opposite, and so there's no potential difference across the resistor for infinite time. All right, so this section 5 in chapter 7, that's something you will find on the homework and on the next midterm exam. So make sure you have these equations written in your notebook, so you have them handy, and put them on the equation sheet for the exam.